In the last part, let's review the question discussed in the beginning of this lecture. We want to find the steady-state solution of IT, ULT, and URT. This is the equation. Now we express all sinusoids with the corresponding phasors. UST corresponds to phasor US, IT corresponds to phasor I, and di over dt corresponds to j omega times phasor I. The corresponding equation is um over the square root of 2 psi u equals r times phasor I plus j omega L times phasor I. And it equals r plus j omega L times phasor I. This is the algebraic equation of I with the complex coefficients. The difficulty of solving this equation is much less than that of solving the differential equation of IT with real coefficient. We can easily get that phasor I equals um over the square root of 2 with a phase angle psi u over r plus j omega. Further, r plus j omega can be written as the square root of r squared plus omega L squared with phase angle arctangent omega L over r. Then we get that the corresponding phasor is um over the square root of 2 times the square root of r squared plus omega L squared with phase angle psi u minus arctangent omega L over r. The time domain expression of the current is IT equals over the square root of r squared plus omega L squared times sine omega t plus psi u minus arctangent omega L over r. By comparison, you will find it's the same as the previous result. Previously, we need to make differential to sinusoid to get ULT. The differential of sinusoid corresponding to j omega times the sinusoid in phasor form. So UL equals omega L times over the square root of 2 times the square root of r squared plus omega L squared with phase angle psi u minus arctangent omega L over r plus 90 degrees. Here the addition of 90 degrees corresponds to the positive j. After getting the phasor UL, we can easily write out the time domain expression of UL. According to the mapping relationship, by applying KVL, we get URT equals US minus UL. Since we've known the phasor of UL and US, we can do subtraction of the two complex numbers by calculator. Although their expressions are complicated, their subtraction becomes simpler after they are transformed into the form of the real and imaginary part in calculator. You can think about it after class. So if the excitation of a dynamic circuit is a sinusoid, the solving of any steady-state branch variable is called sinusoidal steady-state SSS analysis. After listing differential equation of the circuit, we can transform all time domain variables into the phase forms. In other words, the differential equations are transformed into algebraic equations. The method of applying resistive circuits can be applied now. The only difference is that the variables' coefficients are real numbers in resistive circuits and they are complex numbers here. In this lecture, we still need to list the differential equations of the whole circuit to get the corresponding algebraic equations. We will introduce how to write out the algebraic equations directly according to the circuit later. Well, this is the end of this lecture.